So we know how to find the slope of a function. The slope of a function is the derivative of the function. But what if, hypothetically, what if I wanted to find the slope of something that wasn't a function, right? It still has a slope, no problem, right? There is, you know, if the slope at that point right here has a tangent line. All right, maybe I want to find the slope at a point over here, right? That has a tangent line too. So today we're just going to be talking about what happens when we want to, what happens when we want to find the derivative or the slope of something that's not a function. It fails the vertical line test. All right. That's what implicit differentiation is all about. So here we go. It's just the chain rule. The chain rule is just the generalized power rule is just the chain rule. The chain rule is really just implicit differentiation. It's all tied together. All of this stuff that we're talking about a single math class somehow magically relates to each other. What a coincidence. So if I have the derivative, let's say we're looking at the derivative. That is a very short d. The derivative of some function y raised to a power. So, right, we know the power rule. The derivative with respect to y of this is just r, y to the r minus 1. But what if we take the derivative with respect to x? Okay. Well, you kind of use the power rule just like before, but this inside is a function, so we have to use the chain rule and multiply by the derivative of the inside. We have to multiply by the derivative of y, which is dy dx. But it really is just the chain rule. Derivative of the outside function, leave the inside alone, multiply by the derivative of the inside function. So that's what we're going to be calling implicit differentiation. Okay, so let's do some examples and then we'll visualize things in the next video. Find dy dx for the following. Part A, x squared y to the 6th equals 1. This is not a function. This is not a function, but we can use implicit differentiation. So what we're going to do is we're going to ddx both sides, which really is what happens when we take the derivative of a function normally. The right-hand side we take the derivative of, and the derivative of the left-hand side is y prime. But this isn't a function, we'll do it the same way. So the derivative of the left-hand side, that's going to be using the product rule, 3.1. This will be our f, this will be our g. The derivative of the right-hand side is nice and easy. Derivative of the right-hand side, 0. I'm gonna have to move this over a little bit. So product rule says derivative of the first, which is 2x, times the second function, plus the first function times the derivative of the second function. The derivative of y to the 6th with respect to x. We're gonna have to use this up here. Maybe go off to the side real quick, right? The derivative of y to the 6th with respect to x. Use that thing up top. Chain rule. 6y to the 5th. Multiply by the derivative of the inside. Sometimes we'll write it y prime. Sometimes we'll write it as dy dx. Remember, they are the same thing, y prime and dy dx. Either way, we're going to do 6y to the 5th times y prime. The danger of using y prime here is make sure your prime doesn't look like a 1. So now we need to solve for y prime. So first step is ddx both sides. Next step, solve for y prime. So let's lump on over this term. This term doesn't have a y prime, so we need to lump it over to the right-hand side. So our right-hand side is now negative 2x y to the 6th. And we can simplify the left-hand side, the remaining thing a little bit, right? This is 6x squared y to the 5th times y prime. So if we want to solve for y prime, just multiply by or divide by the thing next to it, right? We get y prime is equal to negative 2 x y to the 6th divided by 6x squared y to the 5th. Do a little cancellation and we are going to be good to go. Right? That simplifies to negative a third. Or hold on. We got a lot of stuff going on here, right? 2 over 6 is 1 over 3. X over x squared, this x cancels with one of them. And then all 5 y's cancel with 5 of these. It looks a little confusing. We have negative, all that's left in the numerator is a 1y. All that's left in the denominator is an x. So this is our slope function. Well, it's not really a slope function. Yeah, it kind of is a slope function of two variables. This is how we find the slope. This is the derivative. So notice the derivative depends on y now. And the reason it depends on y is because it's not a function, right? Oh, I was going to show you the previous page, but there is no previous page. It's over here, right? Look over here at this graph on the top, right? The slope at this blue point on the bottom is going to be different than the slope of this one here. So the slope should depend on y, right? This is going to be a negative slope up here, whereas it's a positive slope on the bottom. Let's do another one, okay? Part B. B as in the best problem. Let's do x times y plus 2 to the 5th equals 8. We want the derivative of this. Again, we're going to take d dx both sides. The derivative of both sides with respect to x. Then we'll simplify and solve for y prime. So we have the same situation as before. We need to use the product rule. This is going to be our f, and this is going to be our g. So let's go off to the side, right? What is g prime? 5. Inside stays the same. Lower an exponent. Derivative of the inside with respect to y would be 1, but we're taking the derivative with respect to x. Derivative of the inside with respect to x is going to be y prime. So already gotten a lot of colors here. So derivative of the first function is 1 times the original second function, y plus 2 to the 5th, plus the first function times the derivative of the second function, which we already found to be 5, y plus 2 to the 4th, y prime. Derivative of the right-hand side is 0. Right, again, this is just f prime here, and this is f. This is g, and this is g prime. And that's the product rule, remember? F prime g plus fg prime. Now we solve for y prime. So let's clean things up a little bit. Right, this first term is just y plus 2 to the 5th. The second term is 5x times y plus 2 to the 4th. We'll write the y prime at the end. The y prime is what we want by itself. So just like before, right, we're going to subtract over this term and then divide over by what's next to the y prime. So we get 5x times y plus 2 to the 4th, y prime, equals negative y plus 2 to the 5th. Divide both sides by y plus 2 to the 4th with a 5x as well. We get y prime equals the right-hand side, divided by what we divided by. And as long as y is not equal to negative 2, I should have commented on this before, right? When we cancel back here, we're sort of modifying the derivative, the domain a little bit, right? This domain is not defined when x or y is 0. We should really be specifying that y can't be 0 here. If y is 0, there's no derivative. We'll see what that looks like in a sec. No, we'll see what that looks like right now, okay? So I claim that this derivative is not defined when x or y is equal to 0. That's my claim to you guys. Let's look at it, okay? The derivative is not defined when either x or y is equal to 0. What does that graph look like? It's x squared times y to the 6 equals 1. Oh, look at that. This is certainly not a function. This fails a vertical line test for sure. When x is equal to 0, yeah, derivative doesn't exist. This thing is approaching vertical. It's shooting off to infinity. The function doesn't even exist here, actually. And when y equals 0, again, the graph, not even a function. The relationship doesn't have any value when y equals 0 either. We got an asymptote over here. So it turns out to matter because the function's not even defined at these places, but it's a good habit to be in. All right. So again, as long as y is not equal to -2, and again, this is going to be the same situation where if y is -2, the function's not even defined. As long as y is not equal to -2, we get some cancellation. So 4 of these will cancel with 4 of these. We get that y prime is equal to -y plus 2 divided by 5x. Again, this is as long as y is not -2. I won't be requiring this. This is optional. It's a good habit to be in, but I won't be requiring it. There we go. We found our slopes. Implicit differentiation, finding slopes of things that are not functions. Stay tuned for the next video.